Happy to have Benjamin and Doyon give the second talk.
Yeah, thank you. So, today I'm gonna continue then what I explained last time, and go further. So last time was about Euler-scale hydrodynamics, and now I want to go further in two different but connected directions. One is a diffusive scale, which is kind of the main thing, and the other is correlation functions, not just one-point function. These two things are connected. So just to remind ourselves the setup, right? So we have some state that depends on some large parameter, macroscopic scale L, and it's of the form exponential, say, sum over all the constants of quantity. There's some generalized temperature that depends on position, but that depends slowly on position, x over L, multiplied by conserved density, here I have x. Yeah, so this is our state, our setup. Then I'm going to take the same state, same setup, but ask different questions. So we were looking at local observables evaluated at space-time point, which are far in space-time with the microscopic scale L, same as this L there. And this goes like the average of this observable within the state, which somehow has reached maximal entropy. Sorry?
So this is what the station measure? I mean, the starting...
the same thing, yeah.
State?
Yeah, the starting state, yeah, sorry, there's an L there. Starting state, and then I evolve in time on my local observables. And I said last time that this goes to some maximal entropy state that depends on the betas. Betas depend on x and t, but this is not the same as this, right? And then the relation was...
Fully integral.
Yeah. Is it integral? Oh, sorry, thank you, yeah. Integration of the x, yeah. And then there was this relation that these beta that depend on two parameters, if I evaluated them as 0, I get that beta that depends on a single parameter that's in here, which is the initial condition. Integration. Yeah. So this was kind of the starting point, and everything goes from there, essentially, right? Okay, so now what I want to do is to say, okay, what are the corrections to that, right? So this goes like, we say, equals, I do the same scaling, right? I do the same ballistic scaling, but I want corrections to this. So I could ask different questions. I could ask about diffusive scaling, put some L square here, go far in time. It's different question, different things you could look at. And that's also interesting. But I'm looking at ballistic scaling only, and then in this case, whatever diffusive effects or other effects are going to come into corrections to this larger limit thing. Okay? And the corrections, well, I don't know a priori what they look like, but in integrable systems and also in higher dimensional systems that are not integrable, diffusive correction would correspond to higher derivative, and higher derivative gives 1 over L power. So I would expect something like that. Oh, diffusive that depends on xt with the 1 over L. And the question is, what is this thing? Right? So if you think it's a diffusive effect, you would say that maybe there is some kind of diffusion matrix or something, or some diffusion coefficient, some di, and this is proportional to dx of this beta, say beta, okay, say di dx beta I of x or something like that. So some derivative of the state at time t, okay? Some derivative expansion. So you may get some derivative expansion for what this is going to be at large L. Okay? This is question mark, let's say. Okay? It turns out that it's not exactly that. We'll be connected to that. I mean, somehow close to that. Okay? But that's the first question. Make clear first question. Yeah. And the second question is, well, we don't have to look just at correlation function of a single observable, but we can take 2 of them, or many of them, and ask about how these scale with L when L is large. Okay? Now here for the 1-point function, I said the limit large L exists and is this. But for connected correlation function, maybe I put my comma there if I remember. So these are like the cumulants, right, that Denis talked about also in his talk, right? Connected correlation function, where I would expect these things to decay when L is large, because all the points are far from each other and things should decorrelate. Okay? How do they decay? Is the first question. Well, it turns out that the decay, and I'll explain a bit why, it turns out that the decay is exactly the same as the one that we saw in Denis' talk. which is the large deviation kind of decay. So it will be in L to the power 1 minus n times some function, which depends on the observable, so O1 up to On, and on the points, x1, t1, up to xn, tn. And the question is, well, why is this decay, and what are these s? Right? And it turns out that in the integrable system, this diffusive thing there, and also the higher corrections, are related to these functions. In fact, are can be well, this OZIF is exactly equal to an S with two observables evaluated at a particular point. So there's an equality between this and that. So this controls the diffusive the expansion 1 over L of the 1 point function. And you have, in fact, this whole thing. So you have, say, 1 point function goes like order 1, and then there's a L minus 1, L minus 2, etc. For the 2 point function, it starts with L minus 1, then a correction L minus 2, L minus 3, and these two are connected. And for the 3 point function, it's going to start with L minus 2, and then correction L minus 3, etc. And these three are connected. This is how it works in integrable systems. Okay? So we've developed that bit, but we kind of know in principle how to do the other ones, but it hasn't really been done. Okay? So this is the structure. Now, I will start with this, okay, just to explain a little bit, explain the basic stuff and give you the main formula, and then I'll go to that once I have done this. Okay. Yeah, question about. So why is this L to the power 1 minus n? So why does it decay like the 2 point function like L minus 1? In fact, first thing perhaps to say, what is the meaning of this equation? So if you do it's if you go to computer and calculate dispersion function for the hard rods, you will find exactly this decay. So 2 point functions, you go on computer, you do this large scale analysis of 2 point functions. Now you find 1 over L for the 2 point function, 1 over L squared for 3 point function. But if you take in general something which is not integrable, or perhaps you take the hard rod model with a finite number of velocities, then you might not find exactly that decay. You will find some other power law. But this decay still holds if you understand this equation in terms of distributions. In other words, what I really mean is that I should integrate this here, again, some Schwartz function or something like that. And on the right-hand side, what I'm going to find is really that decay for some distribution that I have to establish. And I'll give you some example of that, what is distribution. So this is correct in terms of distributions, not necessarily in terms of specific functions. And
which class of operator? They have to be neutral with respect.
These, yeah, so indeed, this is for some classes of operator, this is just 0. So in principle, this is every local operators, but for certain operators, this is not the correct leading scaling, and you have stronger decay. And which class of operator is those that overlap with conserved densities? So neutrality is part of it. Yeah, if you have this spin or something like that, yes. So for other operators, you may have exponential decay. It's interesting. Maybe the physics of that. Imagine 2 point function, right? You have some O1 there, some O2 there. I mean, the basic physics is that when you do a 2 point function, you kind of the one of the operator disturbs the system a little bit, and then there's some modes that propagate at some velocity. Some hydro mode propagates some velocity, and this is what this other operator O2 is going to read off or kind of feel, right? And this is what produces the correlation. Right? If the mode propagates, the mode is some kind of disturbance of the fluid like that may grow in a certain way. This diffusive, it will grow like square root of t, super diffusive in some other way. And so what you're going to see is strong correlation exactly at the velocities corresponding to sound velocities of the system, and no correlations anywhere else. If you go on the large scale limit like that, what this function will tell you is that you have a delta function where you have the velocity and you have nothing anywhere else. So this will not tell you about the precise way that this correlation expands diffusively or anything else. It tells you about the overall integration of it. So you have to think of it in terms of kind of distribution. Okay. So I give an example. Now, why the scaling? I give you maybe a simple argument for why this is the right scaling. Suppose I want to do operator at Lx and Lt, and then some constant quantity at 0, 0. And I want to do that in that state there. Okay. So I want to put the conserved density at time 0. Of course, I would like to put them at other times as well, but just as an example. How can I do that? A simple way of doing this, right? This is my state. So why don't I do a functional derivative with respect to these parameters in the state to bring down this Q, right? This is Boltzmann weight. The functional derivative will bring down it. So this I can write as functional derivative with respect to, let me write this here more simply, exponential minus sum over I, can change variable, put at L there, and the beta I of x, qi of Lx, dx, and it's exactly what I want, this qi of Lx. I can put it at x prime or something, but okay, so here I do functional derivative with respect to beta at 0 of this average at Lx Lt. Now, if I take the large L limit of this gives me that, so this is finite. So that goes to O at beta of xt. Okay. Here there's no other scaling, but when I take the beta functional derivative and bring down L, simple thing, right? So I get L times the functional derivative with respect to beta of 0 of this O beta of xt. Okay. And that tells me that this goes like this is not correct, right? Yeah, so I have to do, sorry, L is there. So this is that and is that. Thank you. So I do indeed find that L times the 2-point function, connected 2-point function, is the derivative of this 1-point average respect to beta. So the 2-point constant function should behave like 1 over L, which is the correct scaling here. Okay? Yeah. It also gives me a way of evaluating it, right? If I know solution to our equation and evaluate the observable at that solution, I take a different derivative of that solution with respect to the initial condition, I get the result, right? So, but for now, I'm not going to do that. Okay. So, questions about this? And okay, it's morning. Maybe there's a minus sign here because there's a minus sign there. It doesn't matter too much, so there's a minus sign there. Yeah.
This formula here with M1 minus A, it works also if the O are conserved charges themselves?
No, so this is supposed to be completely general, not just for conserved densities.
But does it work for conserved density?
And it works also for conserved densities, exactly. So this is, yeah, so it works for any local observable that overlap in appropriate fashion with the conserved densities, and actually overlap, I'll tell you precisely in what way this is needed. Okay. So this is just, this is just a particular example of that thing. It's just a particular example, but you can argue similarly for any endpoint function of arbitrary observables. Okay? And then you get this L to the power 1 minus n. And yeah, okay, other questions. Okay, now what about this this SO? Well, this little picture there is something that is quite well known, and if you look at the 2-point connected coefficient function, say this one there, like O Lx Lt, and then Qi, say 0, 0, okay? There's a way of understanding that in a physical way. So I can, here I'm evaluating that on this non-stationary state. But if I go in a stationary state, say beta, right, then I can think of this coefficient function as being a correlation between a variation of O above the stationary state at Lx Lt and variation of Q 0, 0. Now these delta O, the small variation on top of stationary state, there's a kind of a, well, we see from this small derivative expression that we can think of delta O as being essentially like a delta Q, a variation of the charge, but up to the derivative of, because we do this differentiation here, of O of the average over with respect to density. So there is a formula there that people have been using for a long time in hydrodynamics, which is delta O, small variation whose correlation I want to evaluate. I can express it by derivative expansion. So I'm imagining that the observable is a function of the Q because of this relation, right? So I'm imagining that I have this stationary state where there's the density takes certain values, and then I change a bit these. I modify these density a little bit. I mean, I do a little kind of a hit on the state there. Okay, and if I change it a little bit, well, O will change a little bit in function of Q, and in the derivative expansion, and then I just so my small modification is do dq delta Q. And that would mean that this is nothing else but d over dqi, and I have sum over I here, sum over I, and then I have delta qi lx lt, delta q, I'm gonna have perhaps j here, delta qi 0, 0. Okay. So that gives me a relation between this correlation function, and it translates into a projection formula for these amplitudes. It says that S O QI is sum over J D over dQj S QJ QI. So if I know how to evaluate these S's for the densities, I know how to evaluate them for the local observer. Yes.
This derivative DO, DQ, they are evaluated
in the stationary state, yeah. In the stationary state where this is evaluated. Exactly. Yeah. So it's stationary, yeah. So independent of X and T, yeah. So this O bar, and so this is O bar is the average of O in that stationary state, and Q bar is the average of QI in that same stationary state, and that can be inverted. Beta I is a function of the Q's, and then this is what is put in here. This is the usual inversion, yeah. So this is the projection formula for two-point function of local observables. And this is useful, it's very useful, because I can then use that to exactly evaluate this two-point function. Right? So if I believe in this projection formula, I can use that to evaluate two-point function. How it works, you say, okay, let me write the time derivative of qi qj. I'm not going to put the x and t here, right? So they are all there. So one is at position xt, the other is at position 0, 0. Well, I know that this satisfies conservation law, so it will be the time derivative of x, ji, maybe I put the k there, qk. So dt of that plus dx of that equals 0, just by the conservation law. Right? dtqi plus dxji equals 0. So I just put these conservation laws inside the correlations, and I get this relation for the s. Sorry? There's no contact term for the correlation function itself. That's models, not quantum field theory. In quantum field theory, you don't have contact term there. But you may worry about this. We're going to do the scaling L. Yes. But avoiding equal point, that should be correct. Yes. So then I have to worry about what happened equal point, initial condition. But this is fine avoiding equal point. And now I say that I can project this. So this is sum over L, say del O bar del Q bar L times S Q L Q K. Again, this is evaluated in the stationary state, so it is independent of x and t, right?
You should not put index L.
Oh, because I have L. Yeah. What about A?
You have been able to see that it was the L.
What is an L? A. dq bar A, dq QK, right? This is okay. Yeah. So so now this is independent of x and t. This is dependent of x and t, this is dependent of x and t. So I can solve that, right? So S, Qi, Qk, it's easy to solve this, is, sorry, this is a J, right? This is Ji. This is an operator is a J here, okay? And the solution is as follows. So this is dt of something plus a matrix dx of something, right? I know how to solve this, right? This is delta function of x minus that matrix times t. And that matrix is exactly the matrix that Patrick introduced in his talk, First Jacobian, the matrix, the derivative of the currents with respect to the densities. So A, I, A is D, J bar I, D, Q bar A. This is the solution up to some initial condition, which can be a matrix. And so that tells me exactly what the two-point function of constant densities look like in terms of taking that scaling limit and in terms of distribution. So this is a delta function of matrices, meaning that you have to, of course, diagonalize the matrix, take the delta function of the eigenvalues, and all that. And this C matrix, what is it? Well, if I put time equals 0 in this S two-point function, so I have a Qi x0, Qj 0, 0, and I want to look to see what it looks like at large scale. Well, then I have to consider the correlations in the initial state, right? Correlations in the initial state. And this matrix is nothing else but the matrix of correlations in the initial state. It's also the matrix that Patrick introduced. So this C matrix is the matrix of correlation Qi, Qj, connected correlation function in the initial state, well, in the stationary state at equal time. Right. Right. And here we take, this is the matrix of correlation, which involves the total space integrated two-point function, because this is to be seen as a distribution. So you have to integrate over Schwarz function there. Schwarz function of macroscopic parameter, so you take total space integrated. So this kind of a projection argument allows us to exactly evaluate the two-point correlation function in the stationary state for any conserved densities. Okay? Yeah, questions about this little derivation? This is a general formula so in particular, what you see is that you have a delta function at the eigenvalues of the A matrix. That means that the spectrum of the A matrix corresponds to the velocities of propagation of the sound modes. This is where you have non-zero strong correlation, delta function correlation. You can specialize that to an integrable system, for instance, to the hard rods. Maybe I can erase this now. It's this. And because the A matrix and the C matrix and all these things can all be evaluated using thermodynamic methods and all that. And what you find is that if you have two conserved densities, xt, uj at 0, 0, connected, so you look at large L, okay, at large L. Yeah. Yes?
If you put t equals 0 in your formula, you get just delta of x.
Yeah.
What does that mean?
That means that, so that means exactly that. So that looking at this two-point function at large scale is a delta function. But this is, of course, at large scale, right? So like I don't see imagine that you put your sheet of paper very far, you don't see the structure. So that means that correlation at equal time is non-zero only when the positions are very near to each other. And this correlation is, this is natural because in these states, correlation functions decay typically exponentially at large distances. And so this is kind of a representation of this exponential decay of correlations at microscopic scale. So at large scale, you just see delta function. So if you think of it in that way, what do you have? You have operator at Lx times 0, operator at 0, 0. You say it decays like 1 over L times something. But in fact, if the points are exactly equal to each other, it doesn't decay, right? It's just a finite thing. So what you have to multiply by is something that's infinite, which is the delta function. Right? The way of thinking is that if you integrate that over x, you get the total charge corrected with the one point charge. And that's just the total space integrated correlation function of the initial state, which is finite. And that's the C there. That's the C. So the C is coefficient of delta function, representing the total weight of this correlation. Make sense? So that's how it works, yeah. Okay, so so this can now be worked out in integrable systems, and what it comes out to, you diagonalize the A matrix and all that, so you have to integrate over all the possible momenta of the hard rods. There's a delta function x minus v effective t. Okay. So this is the x minus at. And then there's a few a few things. There's a density of the particles, and then there's some dressing of whatever amount of this conserved quantity is carried by each particle. So there's hi dress and hj dress of theta. And this, if we can do the integral, you see that it goes like, there's one over L here, it goes like, one can do the integral and you see that it's no longer a distribution, it's just an ordinary function. And then you see that the correlation function decay like 1 over LT, which is indeed what one can observe in numerics. Okay, so this is for the hard rod. These functions h of theta, hi of theta, j of theta are whatever conserved quantity is carried by each particle. If this is the energy, it's going to be theta squared over 2. Momentum is just theta, etc. Okay. Other questions about this? So maybe I tell you. So in fact, it's what I need. I don't need a lot more than that to go to the diffusive scale. But just to tell you that there is actually. Well, I need a bit more, but not more than this projection. There's actually a general formula for the projection. So any s with any number of greater at different points can be written as some s of q's. So there's a sum of product of s of q's at different points with coefficients which are derivatives like that one. Okay? So there's a general formula of projection for any higher point correlation function. Okay? And there is a kind of combinatorial way of evaluating it. And maybe I just tell you in like 5 minutes what exactly this combinatorial way. So there's a precise formula. So the formula is like that. So you imagine that you have positions there. So x1, t1 up to say x4, t4. Okay? 2, 3, 4. And you have to make groupings of these positions to produce these SQs and evaluate the coefficients in terms of derivative. And the way it works is that you make groupings which cover the whole set in a particular way. So they should cover the whole set in some kind of minimal way. So you kind of produce a patch that covers a subset. And then the next patch you put on it, it should intersect with the previous one just at one point. And then you put the next patch. The next patch should intersect the previous union at one point. Then you put 2 patches like that. And every patch, you associate to that a correlation function of conservaticity. So here I would have SQI, QJ, X1, P1, X2, P2, every patch. And here I will have S. I put some other variable Q A, QB at X3, T3, X4, T4. And every vertex, when you look how many patches cover it, and you put a derivative of your O's for that vertex. So for that one, I would have derivative of O3 with respect to the index that corresponds to that, DQA. For that one, I will have the derivative of O4, but since I have 2 patches, I will take 2 derivatives. So respect to Q, and then for the index is here QB, and the other index for that patch. So that patch might be, SQRQS of X2, T2, X3, X4, T4, and I will have DQ S. So the 2 indices that correspond to X44. So you have derivative for these vertices, SQs for the patches with corresponding indices. You take the product over all the patches with the derivative, and you sum over all possible coverings of this type, which are minimal. So where every patch that you put, every new patch you put, intersect with the previous union only in one point. And that's the general formula for the projection of any number of fields. Sorry?
Be connected.
Yeah, sorry. The patches should all be connected. Yes. So this is a minimal connected covering of this set. Minimal in the sense that it intersects the least possible connected in the sense that how the whole set of patches is connected. And so this is the general formula for the projection of any number of observables, correlation functions or amplitude for any number of observables on conserved densities only. And then by this kind of technique, you can, in this way, evaluate, solve this kind of equation and evaluate your correlation functions or amplitude for conserved densities for any number of conserved densities. So any correlation functions you can evaluate exactly. So there are explicit formulas one can get just doing this projection, writing the evolution equation, and you get in principle all the correlation functions for endpoints at the order scaling. Yeah. Question. So one example, I mean, it's one has to work out kind of all the details of that. But one example, which I will not explain in all the details of stuff, but if I have one conserved quantity only, so not integrable, just single conserved quantity, okay? Then I can look at the 3-point function. Yeah. So the 3-point function of the single conserved quantity at 3 different points, that's going to be some coefficient times delta function of x, x1 minus v, x12 minus v, t12, times delta function x13 minus v, t13, and then there will be some delta prime appearing. So the derivative of the mole velocity times t1, delta prime x12 minus v t12, delta x23 minus v t23, plus cyclic permutation of that. So there's an explicit formula for 3-point function of any hydrodynamic system with a single conserved quantity, except whatever, right? Which involve the function, the prime function is valued in the sense of large-scale ballistic scaling. Right? And this is just obtained by doing this projection by solving this equation.
Product.
Yeah, so product delta times delta minus this product plus cyclic. V is the velocity of your mode. V prime is the derivative of the velocity of your mode that with respect to the conserved densities. And that's in principle is kind of universal formula coming from this. Okay. Now, where does that come from? And how is it connected to diffusion? So, well, but before, any questions about this? So it's just a formula, right? I just tell you this is how one evaluates it. But where does that come from? Even this, for the 2-point function, I didn't tell you very much why is that. So I just said this is this, right? And this is the formula. Where does all the whole thing, all this thing come from? And that's the question. So there is one principle that one can use to evaluate these correlation functions and also to evaluate diffusive corrections in one-dimensional systems. It's an integrable system, okay? And this principle is really at the basis of all of hydrodynamics. Okay? And it's a kind of principle of projection. It's a principle of a reduction of number of degrees of freedom, right? And this is kind of at the basis of everything. Once you accept that, then you can calculate everything, including this type of stuff, okay? The projection, everything, okay? So the principle is very simple. And it's following. So the principle here is to try to separate fluctuations and correlations of local observables from fluctuations of conserved densities, because they kind of happen on different scales. So it's a separation of scales, as usual in hydrodynamics. Okay, so I give a picture. Suppose I have a model of particles in hydro or whatever. It can be non-integrable. Okay, this is my particle. These points there, particle, and I'm taking here some subset of the system. The state is slowly varying, like the state I had, right? And taking here some subset of the system. I mean, something of length L. Say my length L is much smaller than the macroscopic scale, but much bigger than anything microscopic. I would like to take it as near as possible to this macroscopic scale, but it's kind of smaller. Okay? Since it's smaller over some time, that's going to look that's going to look homogeneous, right? It's going to be kind of look nice, but still a lot of stuff happening, right? As time goes forward, the particle move around, a lot of stuff happening. Okay? Then what I want to do, I want to evaluate the averages of observables in here. So I do something like that. Like I call this O bar again, but now it's slightly different meaning than what that had. So it's 1 over L integration over that between, say, minus L over 2 and L over 2. Integration over, say, I call this Y, okay? Then I evaluate this observable, this X and T, okay, at large X plus Y and large T, okay? So the thing that I'm looking at here is far in space-time, okay? And it's degraded over some region which is big but not too big. It's an average like that. Now this is useful to do because if I want to evaluate correlation functions as distributions, I want to integrate against Schwartz functions now. So that kind of already does this integration, bit of the integration with Schwartz function, right? This is integration over space. So that's kind of the right thing to do for that scaling analysis. Okay. Now, what happens for conserved densities, Qi bar? Suppose I look at the time derivative of such a thing. Okay? Now, the conserved density satisfies conservation law. So dtqi is going to be dxgi. So I can do integration of this derivative, and I'm going to get something like 1 over L ji at minus L over 2. Well, there's a kind of Lx minus L over 2 Lt, right? Minus ji at Lx plus L over 2 comma Lt. So I get surface term. So this is small. It's 1 over L. So the time derivative over conserved density is small. So I can assume that over a finite time, the average conserved density is not changing. It's fixed. While if I look at what happened for O bar on finite time, then I'm not going to do calculation, I'm just going to say by words and by picture. Well, if O is not a conserved density, then it changes whenever two particles interact. And you mentioned the particles move around, right? Then there's some interaction. If these two particles hit each other and change their direction, something that is not conserved will change its value. Something that's conserved will not change its value because something that is not conserved will change its value. For instance, if my observable just counts how many particles there is in a certain radius around this one, well, that will change whenever kind of particle interact. So there will be a lot of changes. So if I look on finite time, it's going to be kind of looking very rough like that, okay? Finite time. And there will be about OL changes. It's just some words, right? There will be a lot of changes. So you could imagine that this O bar, then because of all these changes, is going to, maybe if you do a little averaging over finite time, is going to average to its micro-canonical value for these Qs. These Qs don't change while this changes. So this should go towards large time, perhaps under small microscopic time averaging. Its micro-canonical value, which I had denoted like that, so about 1, 2 at xt. So what we say is that no matter how these Qs may fluctuate because of the initial condition, because of all kind of things, these O's, the fluid cell average, this is fluid cell kind of averaging, will be fixed to these fluctuating Qs. Right? And this is the basis of essentially everything. So you kind of separate the fluctuation of local observables which are not conserved from the fluctuation of local observables which are conserved. Right? And if you put that together with the scaling of correlation functions, any correlation function scale like L to 1 minus n, you obtain this. So the idea is that then the average of the correlation function of any local observable, n of them, should go to the average of these random variables, which are variables function of fluctuating conserved densities. So I kind of write it like this. So some O bar now 1 at Q's at x1 t1 up to O bar n at Q's of xn tn. So if I think about my many-body system and I just restrict to the conserved densities and I take the marginal of the resulting measure of the many-body system, the marginal just on the conserved density themselves, then any average of local observables can be written as an average on this marginal. I just have to take the fluctuation of conserved quantities or densities and evaluate these observables as function of these conserved densities within this marginal measure. This is what this principle is saying. Okay. Not a proof obviously, but it's principle. And that principle is sufficient to obtain this general formula of projection. So you have to look at the scaling of endpoint function and with respect to the scaling of the Q bar. And essentially you have to do a decomposition of this connected correlation function of functions of Q's in terms of connected correlation functions of Q's only. So there is a kind of moment cumulative formula that you can use. Okay? So this is the principle, something that we propose, but very much related to a lot of stuff that's been proposed in hydrodynamics before, but something we propose recently in what we call the ballistic fluctuation theory, and then from that we could calculate various types of correlations. This comes out and other type of correlation. Okay? Yeah.
Then you compute functional of the Q bar.
Sorry?
You compute correlation of functional of the Q bar.
Yes.
So why there is only second derivative?
Why there is a?
I don't know, you may have any derivative when you have.
Yes, any derivative, yeah. So the endpoint function goes to n-1 derivative. Yeah. So you see that, you know, the point is, if you imagine that this is like a nth power of Q, well, you have to take, you know, its derivative and then rewrite this connected correlation function into those connected of Q bar, and then you get something like that. Okay? So this is the main principle.
What is the last deviation function for Q bar?
So this is a good question. There, for the initial state that I wrote, is known what it is. In general, the initial state I wrote is known what it is, and it's essentially the.
Once you know it,
sorry.
if you know the last deviation function for Q bar of x and t, you know everything.
Yes, exactly. That's the thing. So indeed, so it's a bit tricky actually. So the last diffusion function for all this correlation in the initial state, we know what it is. It's the relative entropy of Q bar with respect to the state given by the betas. Then the point is you want to know the large deviation function as a function of time.
Yeah. Profile.
Yeah. So then you have to write an evolution equation for this random Q bar, for this fluctuating Q bar. In an integrable system, this is just the Euler equation, because the J's are fixed function of the Q bars like that, and you just have to solve then the resulting Euler equation. In non-integrable system, there are shocks and all kind of things that happen. So then it's something else and it's not written yet because of the shocks. But integrable system, because there are no shocks, then we can write it. So the resulting idea is that the Q bar fluctuate in initial state, and then they are deterministically transported by the Euler equation. And that's how you get the Q bar everywhere in space-time. That's how you can get this stuff and everything else. Yeah. So the difficulty of deterministically transporting this fluctuating Q bar with the Euler equation is that in general, Euler equation, especially for rough initial conditions, there's just not a unique solution. And so then you have to account for the non-uniqueness solution. But integrable system is unique solution, and then it's fine. And this is then the basis, indeed, exactly what you're asking of the diffusive thing. Maybe I'm very late. I'm sorry. No. Still 15 minutes, okay. So now I'm going to the diffusive scale. Okay. So what's the idea of diffusive scale for integrable systems? Well, the idea is a bit, maybe kind of a little bit bold, but okay, it works. Okay. The idea is that this thing just works when all these quantities are very large. You need to converge the macrocanonical ensemble. And for integrable systems, we claim that this actually works to to our order in 1 over L, so even when L is not that large. So just to put your mind around here, so what I'm saying here is that there's a lot of changes of the observable, so it goes to microcanonical value. But what is the correction? Well, the correction is going to be, say, 1 over square root of L or something, right? This is the, you know, correction because I take an average, but it's not that large to have corrections, right? But in integrable system, this correction is L to power infinity. We think, or I think, or whatever. Why is that so? So you can think of it that way. You can say, let me take this finite, you know, L length, a little interval, okay? And then I was saying, well, I can do time evolution, finite time evolution, and there are a lot of changes over L, okay? So then I get this, right? But here I'm using the Hamiltonian that of my original system, but this is an integrable system. So there's an infinite tower of Hamiltonians, and they all compute with each other. So I could as well, I'm using time evolution that way, right? But I could do some other T prime evolution with some other Hamiltonian. A bit of a small, average over this T prime direction. Same principle will hold. This will also change over L. And if I average over this whole little kind of a region T prime, then it will be over L squared changes. This is just physical intuition, right? Now, the more I do average over all the higher constant quantity, the higher the power of the number of changes that they will find. So this is kind of OL. And so then what I'm going to have is 1 over L to the power n over 2, and I can take n as large as I want, and so there's no correction. It's kind of the idea that if I do averages without the constant quantities on finite microscopic time of these constant quantities, then this convergence to the microcanonical ensemble is going to be very strong. And then I can use that for everything. Assume that things converge to microcanonical ensembles. Okay, this is just a hand-wavy explanation. Okay. Now, what do I do with this? So I want to evaluate, so I have dt, I have my conservation laws, my dtq plus dx j. And I can write this conservation laws for the fluid cell averages. Okay. Then I want to know what happens when I take average of that. So in the state, okay. And I want to rewrite this fluid cell average of the current in that state in terms of the average of the Qs, right? This is the thing, okay? But I can use this. So this is the principle, right? J bar I in that state should be well approximated by a fixed functions of all these Qs evaluated at that position xt in that state. Now there's no connected average. This is just one point function. Now the Qs are evaluated at the same point xt. They all kind of fluid set averages of the Qs. And what I can do is something called the cumulant expansion, which is that this, I can expand that in the cumulants of the Qs of higher and higher order. This is good because I know that the higher cumulants decay faster than the lower cumulant. So this is going to be J bar I at the average of all these Qs. Plus second cumulant, third cumulant, fourth cumulant, etc. And it turns out that the next correction is a second derivative with respect to the Qs, and then you get the second cumulant. So Q bar R, Q bar S, cumulant. And then you have higher cumulants being involved. And now I'm using the general principle that the higher cumulants decay faster. So this is going to be of order 1 over L. So the state is, there's an L in the state here everywhere, right? and these are evaluated at far point at XLT and all that. So this is going to be 1 over L, and that is the diffusive scale correction. So in other words, there is no noise in the integrable system. The noise will come from that term there, right? This is when I do this crude-set averaging and say this macrocanonical and say, well, there's corrections. Correction is a random correction, it's a noise in general. But in integrable system, there is no noise. By this argument, this is exact. The only thing that there is that we have to evaluate correction functions of conserved densities, which should be over the 1 over L. Okay. Now, what are these correction functions of conserved densities? Any big questions about this? So correction function of conserved density. So what is that? This is so if I look at Q bar R, Q bar S, okay, Lx, Lt, and this is my Q bar S is supposed to be at the same space-time point, right? It's all evaluated to the same space-time point, but let me put it at Lx prime at the same time Lt. Okay. So I said that this goes like L minus 1, and this amplitude Q bar R, Q bar S, X, T, X prime, T prime, right? This is that. So I need to evaluate this amplitude. And I need to evaluate it at X equals X prime. Okay, that's what I need. Now, I can write an equation for this amplitude coming from this projection stuff that I wrote, right? And the equation is relatively simple, so let me call this just SRS, okay? SRS. All it says that, well, you have to replace Q by J here and Q by J there because it's the same time here, so you have some A matrix that's involved, and some for the first point, and you also have an A matrix that's involved for the second point. Okay. So we satisfy that this equation, this dynamical equation, where this is Flood-Jacobian, and this is the S evaluated there. This one, this Flood-Jacobian, is evaluated at X and T, and that X prime and T. And I have to solve that with appropriate initial condition. Initial condition is relatively simple, it's the same as for X prime 0, it's just delta function X minus X prime times the C matrix, like the one I had before. Okay, but as time evolves, then something else. Okay? And what happens as time evolves? Well, you can solve that in your system. You can write this explicitly and solve that. It's very interesting what happens. So this SRS at different time, it keeps this delta function, and then I have to tell you what I do with delta function. Okay? But then there is an extra term which is not supported at X equals X prime, which is supported away, which is long-range correlation. So something that correlates points which are at macroscopic distances. So at different values of X and X prime are macroscopic coordinates. So there is an extra function that just comes from solving this equation. And this function is what controls the diffusive process. So our proposal is that this thing there, which is 1 over LS RS, okay, at the same point xt and xt, this thing there should be evaluated. Well, actually, if you look at that, you see, well, I have to put the same point here, right? X equals X prime, but there's a delta function, X equals X prime. But there one has to again do a bit of hand waving. There's some expansion one can give, but essentially this delta function represents small scale correlations that are already encoded within the function J bar itself. So in fact, you have to put this at X plus 0 and X minus 0 at slightly different points. You have to avoid the delta function. So you just look at the large scale correlation. This corresponds to large scale correlations. And if you do that in a right way, in an appropriate way, you evaluate this by solving that equation, and you put it in here. This is our proposal for the exact diffusive scale of hydrodynamics in integrable system. Now this is, one has to put some meat onto it, yeah, exact formulas. And we have exact formulas for what this looks like at initial time, at small time, but not what it looks like at later time. Well, there's some formulas, but they are complicated. There are some formulas. Okay? And well, the end result of that is that if we evaluate at time, say 0 plus at initial time to do all that stuff, what we find is a formula. I can write a formula for this term. Right? Find a formula which is, okay, it's a bit complicated, maybe. So we have to go to the diagonal basis that Patrick was talking about, and we find a formula where there is some there's some 3-point function of this diagonal basis quantities. There's an index I, which with the current, with a certain modification of the current connected to prime function, which appears essentially twice. And this is multiplied by some inverse matrix C, and then there's a derivative of the average of the densities, okay? And this whole thing is divided by the difference of effective velocities. Absolute value. So if I put all of that together, I solve for this long range correlation, I evaluate this second derivative, I put it in here, and get everything, I get this formula. This is formula, exactly the formula, at time 0 plus exactly the formula that we had derived with Denis Bernard and Jacopo Donadis, especially with their proposed work, using Green-Kubo formula to evaluate the diffusion constant. So this is the Green-Kubo diffusion matrix. This formula is exactly the Green-Kubo diffusion matrix. Evaluated here in a completely different way, it has nothing to do with the Green-Kubo principle, but it comes back to exactly the same thing if I evaluate all that at a very short time. But at later time, this function, this S, its long range bit becomes completely different. And then the formula that we have for the diffusion then completely different. It's not a Green-Kubo, it's something else. And we check numerically that this something else agrees with Monte Carlo numerics, what the Green-Kubo doesn't if we go to kind of finite macroscopic times. Right? So this is the principle of the diffusive hydrodynamics in an integrable system. It's based on the idea that you locally can project on the conserved densities, and all you have to evaluate are whatever observables as function of this conserved density, which are then self-fluctuating. You vary them with an appropriate regularization where you avoid the functions for a physically motivated reason. And what you're left with are correlations which develop over time because of the nonlinear dynamical equation for correlation functions. And these correlations that develop over time, evaluated at nearby points, are what determine the averages of currents and any other observables in your many-body system. In principle, you can go to higher orders as well. Same principle should hold. I haven't checked, okay? But in that cumulant expansion, you can expand higher cumulants. You can evaluate the higher cumulants by writing their dynamical equation, evaluating the long-range part and put it in here. In principle, it gives you the full 1/L expansion of the hydrodynamics for integrable systems. Questions about?
So
for non-integrable systems, a lot of things fail in what I said, right? For a start, you see in this formula that I obtained, which is valid at initial time, right? We just calculate long-range correlations and all that. You see in this formula that if this particular three-point function, well, I didn't say what it is, if it is non-zero when the velocities are equal to each other, this diverges. And this thing there, which I've written there, is exactly at R equals S, exactly something that Patrick talked about in his talk, is the diagonal part of some three-point G coefficient that we will define. This is what controls super-diffusion. In other words, if there is super-diffusion, this long-range correlation appears to be infinity, and something else happens. So that diffusive correction is not 1 over L, it's another power, right? This is what fails in general. In an integrable system, it turns out that this correlation at R equals S is 0. It just turns out it's like that particular structure of integrable systems, right? Particular structure. There are other models where this is the case, where an R and S J is 0 when R equals S, and when the velocities are equal. There are other models. These are called linearly degenerate models. And in these models, this formalism is correct. That's correct, part of diffusion. But in these models, the assumption that the convergence to the microcanonical ensemble is to all orders is not correct. There can be noise contribution. And so in linearly degenerate model, you have this contribution plus a noise contribution, which will give the standard Green-Kubo derivative expansion. But this is not developed yet. And yeah, and if you go to higher dimension, there's something similar that happens, except this kind of corrections would affect the dispersive part of hydrodynamics in 2D, or the higher order things in higher D. So it will not affect diffusion in dimension D2 or above. Because the correlation will go like to a higher power bell. Okay, yeah, so that's any questions about this? Yeah.
Yeah. So if you do small, you put an integral model and you do small perturbations.
Yeah.
So short time, the system will behave like an integrable model, and at some point we have some deviation.
Yeah.
But here also you have a deviation at the beginning. You have a diffusion like given formula, then you have a deviation.
Yeah.
Can you compare the two scales with this deviation?
It's a good question. Yes. I don't know. Yeah. So I mean, you would have to for a non-integral model, you have to have low enough density so that it looks a bit like integral models and in particular parameter regime. So that depends on that, right? If you have to have low enough density, right? If it's high density and all that. But yeah, indeed. So I guess in these cases, what it would say is that it would start like a Green-Kubo integrable model and then go to super-diffusion, for instance, as you start seeing the non-integrability, say the higher constant of charges.
Yeah, but the question is whether you will see further deviation due to non-integrability or further deviation due to that.
Yeah. So I don't know. I guess it depends on the parameter, right? So if you depend on the density.
It's a way to.
Yeah, it depends on the density, right? If you have very low density or something, but yeah, I don't know. Yes. I don't know. Think about it. Yeah. Yes.
You said this ERS is long range.
Yes.
So how does it decay? Like how does it fall off on x minus x prime?
So these are macroscopic coordinates, right? So it's long range in the sense that this is already at large distances. That's right. And then a particular function, this E itself is not a power law. It's a for initial time. What it looks like actually, it's a relatively simple for initial time. Put it here, right? It looks like it develops. So this is x equals x prime. It develops a front. The front that starts from 0 and it develops. We have a sharp change there and a sharp change there, and the front grows with the difference of velocities vfi minus vf r minus vfs. So this itself is not a long-range function. But what it says is that the correlations are non-zero at macroscopic distances.
So ERS is compactly supported, but it still has support.
So in a macroscopic coordinates, it's proportional to L in that sense, yeah. Then as time evolves, it may get some tails and stuff like that, but I believe it's compactly supported, yes. Other questions? Okay, thank you.